Okay, so I just got back from a concert where they played my favorite song, Wizards in Winter. That's my favorite Christmas song. And I went to the concert because my son Jamie plays the violin when he's not dreaming of owning a food truck. Anyways, I can't seem to get that song out of my head. Tonight we're going to talk about geometric applications, lines in space, and line classification. And I apologize, this is probably going to be a little long, but that's the last video for a while. So the first thing we're going to talk about is how to find where two lines meet. So if I have a vector that's moving, I gotta lock that down, hold on. Okay, so if I have a vector that's moving along this line and another vector that's moving, I don't know, maybe this line, eventually they're going to meet. It doesn't mean they're going to collide, because it might be that they're not meeting, that they would intersect here. They might not be meeting at the same time or intersecting that point at the same time, but their paths will cross. So there's a difference between a collision and an intersection. All right, so my first line has this vector up here, and my line 2, should be line 2, has this vector. And the two lines meet at point P, so let's use vector methods to find the coordinates of P. Well, if they intersect, that means that their x and their y coordinates are equal. So we're going to set, since this equals x, we're going to take this equation here, -1 plus 3r. It has to be equal to this x value at the not at the same time, but it has to have that same value. So those have to be equal. That's going to be our x coordinate. And then our y coordinate, 6 minus 2r, down here, is going to be equal to 2 plus 1s from this equation. Okay, so from the first equation, that looks like a 15, it's a 1s. If I take and rearrange this, I get 3r minus 1s, right? I would subtract 1s from both sides and add 1 to both sides, equals 1. And over here, if I rearrange this equation, let's keep it in the same order. I'd subtract 1s from this side as well, and my constant would be on the other side of the equation, and 2 minus 6 would be -4. So there's my two equations. I'm going to take my second equation and multiply the whole thing by -1. And I'm going to keep my first equation the way it is. And that's going to give me 2r plus s equals 4. Now I can add my two equations, and that gets rid of s, and that gives me 5r, and 1 and 4 is 5. So that means that r equals 1. So I know that the r value is 1. Let's go ahead and find the s value. Let's plug r into, let's try our first equation. So if r is 1, -1 plus 3 times 1 equals 1s. So -1, so that means s equals 2. All right, so in order to, I want to check my equations and make sure they're both equal. Let me erase what I have here so you can see better. All right, in my first equation, if r equals 1, then x equals -1 plus 3, and y equals 6 minus 2, which means that x is 2 and y is 4. That's the point. Okay, if s is 2, then from this equation, x would be 0 plus 2 times 1, which would be 2. And then down here I'd have 2 plus 2 times 1, which is 4. So my point for this line would also be 2, 4. So point P equals 2, 4. And that's where those two lines intersect. Not necessarily collide, but intersect. Here's one for you to try. So I have two equations, line 1 and line 2, two vector equations. S and T, those are scalars, which are just single numbers. So use the two lines meet at point E. Use vector methods to find the coordinates of point E, just like I did before. So pause this when you're ready and turn it back on to check your answer. Okay, hopefully you got the right answer. I'll go over this briefly. Bear in mind, this is going to take long enough as it is, but you set up a system of equations where this x equals this x and this y equals this y, and you're going to simplify it, put them both in standard form, and solve it using elimination or substitution if that's easier. And you get s equals 3 and t equals 2, and then to check it you plug it into each equation and you should get the same point for each equation. If you do, then you've got the right answer, and it comes out that these meet at 7, 7. So that was lines in 2D. There's also lines in space, and so that's what we're going to talk about now. A line in space is a straight line that continues indefinitely in both directions and contains an infinite set of points. So suppose we have this point on the line, it's x, y, z, and it can move anywhere on the line. Of course, it'll be moving on this direction because my direction vector here points that way, and F is a fixed point on the line. So this point can't move, but this one can. Okay, so if B, my direction vector, is a direction, if B is my direction vector, and it's got coordinates A, B, C, those are x, y, and z coordinates as well. And F to M, vector F to M, equals some time times my vector B, right? In my picture it's 2 vector B's, but it could be any value of t. So for some scalar t, then the vector B, my direction vector, is my ending point minus my initial point, right? x2 minus x1, well, this is x minus x0. It's the same thing. So in order to get, so that's going to equal my direction vector, which is my A, B, and C value here. Okay, so I'm just looking for how far and in which direction I'm moving on the x-axis. That's my A value. Same for the y, and then same for the z. That's my C value. Okay, and then this would be my vector equation of a line. X, y, and z at any time is equal to my starting point, x, y, and z, plus time times my direction vector A, B, and C. Okay, so let's put that into practice. I have 2 points. I have A and B, and we're going to find the parametric equations of the line through A and B. So line A to B, that's my initial value here, and here is my second value. And this is my direction vector. So x, y, and z is going to equal my initial value, which is A, to -1 and 4, plus t times, I have to calculate that vector from a to b, so I can look at it either as -1 minus 2, or I can say to get from 2 to -1, which direction? Well, that's -3. Either way is fine. -1 to 0 is 1, or 0 minus -1 is +1, and 4 to 2 is -2, or 2 minus 4 is also -2. And that's my parametric equation of my line. Pretty simple. Wait, that's my vector equation. My parametric equation is x equals 2 minus 3t, y equals -1 plus t, and z equals 4 minus 2t. That's my parametric equations. Okay, so for the next example, it asks for the coordinates of the foot of the perpendicular. So I didn't know what a foot was. I had to look that up, and apparently the length of a line from a vertex of a triangle to the perpendicular foot is called an altitude, and a line drawn from a point to a plane, its intersection with the plane, is called the foot. So it's where your right angle is formed with the base of whatever it is you've got. So now that we've figured out what a little bit of IB language, let's see if we can figure this problem out. So we have a point P, I'm going to call it P, and it's 1, 1, 2. All right, so some point P, and then it goes to a line. I'll call this where it intersects with a right angle as A, but I have some line here that's a vector, because look, here's 1 plus t, 2 minus t, and 3 plus t. All right, so I need the direction of this line. That's P to A. So if I look at that, for vector P to A, that's going to be x minus x0, y minus y0, and z minus z0. All right, and so the x component of my vector is, here's my initial point, here's my second point. So it's going to be 1 plus t, because I'm looking for the second point, minus the initial point, so that'll be -1. The y value is going to be 2 minus t minus 1, and the z value is going to be 3 plus t minus 2. So that means that P to A equals, well, just t for the first one. 2 minus 1 is 1, so 1 minus t. And 3 minus 2 is +1 plus t. So those are my components of vector P to A. Okay, so we also need this vector's movement. If I look at that, the direction of that vector is 1, -1, and +1. I'll call that vector B because that's what we've been calling that direction vector all along. So what I'm looking for is when these two are perpendicular to each other. So PA dot B equals 0. So dot product, I have to multiply the components together. So I have t times 1 plus -1 times 1 minus t plus 1 times 1 plus t. That has to equal 0. So t, I get 1t minus 1 minus, plus t plus 1 plus t equal to 0. Well, my t's are going to, or my 1's are going to cancel out, and I'm left with 3t equals 0. That means t is equal to 0. All right, so if I go back up here and try to figure out where that happens, t equals to 0, well, that's going to be where t is 0 here. So x is equal to 1 plus 0, y equals 2 minus 0, and z equals 3 minus 0. So it's at my initial point, 1, 2, 3. So that is point A. Okay, so I can see on your note sheet it says you try, and so I don't know what I was thinking, because this is not the same problem I wanted you to try. I must have been really tired when I made this note sheet last night. All right, so on your note sheet it says find the vector equation and the parametric equations of the line through 1, -2, and 3 in the direction of 4i plus 5j minus, is that a 5 or 6? Well, I'm going to go with 6. Okay. All right. If you want to give this a shot, go ahead and stop the video and then restart it back up. If not, I'll just go through this because it's in your notes next. So the vector equation would be xyz equals my initial point, 1, -2, 3, plus my direction vector. In this case, that's 4, 5, and -6 times my time. All right, so that is the, why would I do that? Segment. Well, let's find the parametric equation. X equals 1 plus 4t, y equals -2 plus 5t, and z equals 3 minus 6t. Done. Check. It's time to move on to a harder example. Now I'm going to ask you to do something crazy. And jump to your note sheet, the back side of your note sheet, and then we'll go back to the line classification. But the example that was supposed to be next for you to try was the coordinates of the foot of the perpendicular from point -1, 2, 3 to the line with parametric equations x equals 1 plus 2t, y equals -4 plus 3t, and z equals 3 plus t. I want you to give that a shot, and then turn this off. When you're done, start it back up and check your answer. All right, so hopefully you got that t was equal to 1 when you solved your vector, when you found where the dot product equals 0 of your two vectors. And then when you plug that back into your equation, to get the foot of the equation, you get the line is perpendicular and the point is 3, -1, 4. And if we wanted to find the length of the line at that point, we would use Pythagorean's theorem, or magnitude, and we'd get 3 squared plus 1 squared plus 4 squared is going to equal radical 26. That's the shortest distance from P to the line. Hopefully you got that. If not, you're going to have to come see me for extra help. Or play the video over. I don't know which is worse. And so now we can go back to the line classifications. So from geometry, hopefully you remember that two lines in space they have three possibilities. They are either parallel, intersecting, or skew. All right. So if they're parallel, that just means they're parallel, that they never intersect, but they're the same distance apart all the way following the vectors. And if they intersect, they have a point where they cross. Not necessarily collide, but cross. And then skew is when they're not parallel, but they don't intersect either. Okay, so those are 3 classifications of line: either parallel, intersecting, or skew. Okay, so we can use the dot product to tell if things are perpendicular or parallel. Perpendicular is when v dot w equals 0, and that's because cosine of 90 degrees being perpendicular, is equal to v dot w over v w, and cosine of 90 is 0, and this fraction will only be 0 if the top is 0. So that is how we tell if they're perpendicular. We can tell if they're parallel. If you think about this, parallel would mean cosine of 0. What's the cosine of 0? Come on, think unit circle. At 0 degrees, it's equal to 1. So the test for, let me write this down, perpendicular is here. Parallel means that v dot w has to equal the magnitude of v times the magnitude of w. Right? Because this over here has to be the same thing over the same thing in order for it to be equal to 1. So these have to be the same. That's what we didn't think about. The cosine of 180 degrees, that would also be parallel. That'd be -1. So it could also be that v dot w equals negative v w. And that would give me another possibility for a parallel line. They'd just be going in opposite directions. Okay, we must be cooking right along here because I'm already on example 4. Yay! You must be as happy as I am. So I have line 1 and line 2, and we want to show that they're parallel. Means they're the same distance apart and they never intersect. Ooh, what happened to my pen? It looks weird. Let me go back and fix that. Okay, that's better. It was like it's see-through. It's a ghost pen. All right, anyways. If I look at my direction vector for line 1, my direction vector is 2, -2, and 4. So that's line 1. For line 2, it's -1, 1, and -2. If I take a look at this, look at my, if they're parallel, there's also going to be something else that happens. I'm going to have, one has to be a scalar multiple of the other. So 2, -2, and 4, that's a scalar multiple of line 2 if I multiply the whole thing by 2. Actually, -2. That's going to give me the same line here. So that alone shows me that they're parallel. Okay, so I've saved the best for last and for you. I have 3 equations, line 1, line 2, and line 3. You're going to show that line 2 and 3 intersect. So these 2 equations intersect. You're going to need to set up a system of equations and solve for when that happens. And then you need to find the angle between them. So you're going to find the magnitudes and divide it by the dot products. And then you're going to show that line 1 and 3 are skew. So if they're skew, they never intersect. So if you set up a system of equations, you should get something silly to say that it doesn't happen. So turn this off, give it a shot, and turn it back on when you're ready. Okay, hopefully you gave this some serious effort, because this is the kind of problem you're going to actually have to be able to do. It's all very simple math. It's actually all Algebra 1. It just takes a lot of steps and a lot of thinking. But that's my job, is to teach you how to think. Not how to think, but how to persist in thinking. If I could teach you anything, it wouldn't necessarily be math skills. It'd be the grit to stick to a math problem and try it. You know, some mathematicians work for years on one problem and they actually never solve it. So if you had to spend 10 minutes on this, boo-hoo. Anyways, so setting up a system of equations for lines 2 and 3, you should get that u equals 1 and t was equal to -2. And checking in one of the equations, you get a common solution and it satisfies all three equations. So using u equals 1, you plug that into your original equations to get the coordinates, and you get 3, -2, 7 is where they meet. And so the direction of line 2, you take your direction vector, it's -1, 1, and -2, and the direction of line 3, take that vector, and you do the dot product, and you should end up with the angle between them is 169 degrees, or 169.1. And then for the second part of the solution, yay, this is it. This is the last part. You get, you try to set up an equation for 1 and 3, and you should get something silly. They did 4 doesn't equal to -3. Mine, I think, was 0 equals something else. I don't know. But it didn't make any sense. That means there's no simultaneous solution to all three equations, or that there's no place where they all meet. So that's it for tonight. And here's a little Christmas cheer to end the video. Good night. I'm off to bake Christmas cookies.